Alright, so I'm not seeing anyone out there, so I'm just going to kind of sit here and wait till somebody shows up to ask me questions. I'm curious though. But I'm out of this flat. I did. So why is the camera not up? Alright, I'm just going to kind of work an old kinetics problem just because I'm curious if I remember how to do it. But what you're seeing on the board is not anything to do with the test you're taking. It's related to the material, but it's more like an advanced thing. So if you got questions, I'll be looking over my shoulder every now and then to see if anything's in the chat. But yeah, I'm not seeing one in the chat room now, so I'm assuming y'all didn't really have questions today. So SF is significant figures. So if you see SF, so someone's asked, what does SF mean? Whenever you read the review I give you on the test, SF is the number of significant figures. So typically it's about a point off for that. How do we use information in the lessons tab for the concentration versus time homework? So let me bring that homework up. For those of you who are curious where this homework is, if you go to the course website and you scroll down, you go into lessons, you want to do the test 2 material. Come on. You're going to find it down here with data for the web assignment homework, concentration versus time, and pre-exponential factors. So how do we actually do these types of problems? Well, hold on. Excel's having some issues this morning. So when it comes to looking at this type of information, what I commonly see with students is this rush to just plot and give an answer. And it's misleading because you'll get the right answer for the first case, but you won't get the right answer for any of the other cases. And that's more what it's meant to diagnose, is to giving you that. There are 3 kinetic models that we have for measuring concentration versus time, or at least ones that we solve in this course. So one is the zero order. The zero order looks like concentration is starting concentration minus kT. First order is starting concentration, or concentration equals starting concentration, e to the minus kT. And then the second order is 1 over concentration minus 1 over starting concentration equals kT. So, why we use this information? We can linearize it. So the linear form does 2 things for us. First of all, it's a testable hypothesis. So if we have a zero order reaction, if we plot concentration versus time, so concentration versus time, this will be a straight line if and only if it is a zero order reaction. So if we plot concentration versus time and we get a straight line, we know it's a zero order reaction. For the first order, if we plot natural log of concentration versus time, so the natural log of the concentration versus time, if we get a straight line, that tells us it is a first order reaction. For the second order, if we plot 1 over concentration versus time, if this is a straight line, it is a second order reaction. So the first thing these linear forms do is they give us a testable hypothesis. If we take our data, which is concentration versus time, and we create 3 plots, concentration versus time, natural log versus concentration versus time, and 1 over concentration versus time, this will tell us if it's a zero first or second order reaction. So let me show you how you're going to do that next cell. So you're given concentration versus time. The other things we need are natural log of concentration versus time and 1 over concentration versus time. We're going to need 3 plots. So our first plot is concentration versus time. Second plot will be the natural log of concentration versus time. And our third plot went over concentration versus time. Now, to figure out if they're straight lines, what we're going to do is add trend lines. And the 2 things we want out of the trend line, the equation and the r squared. So I've got 3 plots here. I've got the concentration versus time, natural log of concentration versus time, and 1 over concentration versus time. So what I want to do is I want to look at these 3 different models and say, which model does it fit best? Does the concentration versus time look straight, or does the natural log of concentration versus time look straight, or does 1 over concentration versus time look straight? So if we go back to those plots, we have an r squared of 0.9879, 0.9939, and 0.9966. This is the straightest plot, So this 1 over concentration of A versus time being the straightest line means that this is a second order reaction. So we can say definitively this is a second order reaction. Once we know this information, we don't need the other two plots, so we can get rid of them. Now, the second thing our model does for us, and this is something that you didn't see a lot in Chem 1, you're going to see a lot more in Chem 2. The reason we want a theoretical model is that it doesn't just tell us what the order is, it tells us relevant information about the reaction itself. So if we look at this, our y here is 1 over concentration, and our x is time. Well, if we fit y equals mx plus b, which is what we've done by adding a linear regression, we know that the slope corresponds to the rate constant k. So whatever number we get for the slope, that's going to equal the rate constant k. The y-intercept should be 1 over the starting concentration. So if we go back to those plots, it'll make it a little bit easier to see on your end. We get that the slope is 0.0224. That tells us that the rate constant k for this second order reaction is 0.0224. As far as the y-intercept, we know the starting concentration is 0.25. This 0.40227 should be 1 over the starting concentration. So if we take 1 over 4.0227, we get roughly 0.25 back. So this is in agreement with what we would expect to see. Now, some common confusions I see on this particularly are with the y-intercept. It is saying that numerically what you get from x cell is equal to 1 over concentration. It is not saying 1 over the y-intercept is 1 over the concentration. This number b equals 1 over starting concentration, so the starting concentration is 1 over b. If we ended up fitting a first order, we would get that the y-intercept is the natural log of the concentration. So we would need to take the exponential. Starting concentration here is e to the y-intercept. It's not the natural log of the y-intercept. This is not the algebra you're performing on the y-intercept. The y-intercept is equal to the algebra. So that's how you do this concentration versus time homework. You've got to create the three plots. 1 over concentration versus time, 1 over concentration versus time, and natural log of concentration versus time. Whichever one of those is most linear, that tells you the order. From that, you're going to look at the kinetic model. So do your linear regression. The slope here is always the rate constant k. It'll change signs, but rate constant k, because it's a probability, has to be a positive number. So it's going to be the absolute value, whatever the slope is. And as far as the starting concentration goes, you're going to know from the model what the y-intercept corresponds to. Now I'm also going to ask, can you work out number 2 on the orders from graphs of concentrations? So let's bring that up. And let me share my desktop with you really quick. So for number 2, we've got the natural log of concentration versus time. So off the bat, since we're plotting natural log of concentration versus time and we're getting a straight line, that tells us the order here is going to be 1. Because it's only going to be linear for natural log versus concentration versus time if and only if it's a first order reaction. Your slope here, the 0.0234, that's always going to be your rate constant k. In terms of the starting concentration, what we get, flip back to the camera, is that for a first order reaction, our y is natural log of concentration, our x is the t, so our slope is negative the rate constant, our y-intercept is equal to natural log of the starting concentration. So based off this kinetic model, the y-intercept is 1.7935 equals the natural log of the starting concentration. So the starting concentration is e to the 1.7935. And when you work it out, you get around 6.01. And again, I see this mistake a lot with students. You don't take the natural log of the y-intercept. That's not what the model says. The model says the natural log of the concentration equals the whatever that y-intercept is. You have to undo the natural log. Same thing's true for second order. Second order says that the starting concentration is 1 over, tells you the y-intercept is 1 over the starting concentration, so you have to take 1 over the y-intercept. And for a zero order reaction, it's really easy. The y-intercept equals the starting concentration. All right, any other questions? Yeah, you're welcome. We're kind of introducing this concept now in reaction kinetics. This is going to show up a lot more for the next test. We're going to build a model from scratch. The models all have physical parameters associated with them. So we're not just building this for the esoteric exercise of building a model. Ideally, any model we build gives us more information out than we could glean just looking at the data. So by doing these three plots, concentration versus time, natural log of concentration versus time, 1 over concentration versus time, we're doing more than establishing what the order is. We're figuring out kinetic parameters such as the rate constant K. And as you'll find when you start doing the activation barriers, we can also take our rate constant K, solve it at multiple temperatures, and figure out what the activation barrier EA is, because that number is specific to the reaction. So once we measure an activation barrier, we know it wherever we are in the world. We don't have to ever measure it again. And one thing we don't talk about in this level, but I'll introduce if students have the time and interest, is actually we can use disproof of these models to explain other phenomena. So one big one you're going to work with is the Arrhenius relationship, which is where you're going to get the activation barrier. Well, if the slope changes on your Arrhenius plot, it tells you that the rate limiting step has changed. And so you can actually, if you got the resolution, figure out the activation barriers for different parts of the reaction mechanism and see where you can actually pinpoint the temperature where the reaction mechanism's rate limiting step actually changes. And that's basically working by disproof. We know the activation barrier should be linear if we plot natural log of the rate constant versus 1 over temperature. If it's not linear, we know that the mechanism has changed. But that's the power of building models, is it gives us a testable hypothesis. It's something that we can work with. Now, another thing to keep in mind with the homeworks, hopefully you saw this when I worked these two examples. Several of the homeworks give you the data pre-processed, and so they say, okay, here's the plot, give me the information. That Excel homework is just the next step up. You're generating the plots, and then you're going to do the analysis that you did on the other homework sets. So these homeworks are meant to build in complexity, but so that you can see how the pieces play together. In a lab setting, you don't measure natural log of concentration versus time. You don't get a plot that looks like that. You get concentration versus time. That's what you measure directly. And in a typical seated lab, we actually have one lab where you do that. You acquire the data and you do the 3 different plots. So this is more trying to keep you from getting locked, considering the theory and the experiment as separate pieces of what's going on. The theory gives us a framework for analyzing the data, but there is a practical side of it. When you get the data, it's generally not in a useful form. You have to manipulate the data, and I shouldn't say manipulate, it's the wrong connotation. You have to process the data in such a way that it's in a form that's useful for comparing it to the theory. So in that sense, the Excel homework is a lot more realistic representation of what you would see. You would not get the homeworks that had natural log of concentration versus time, what's K, what's starting concentration, what's the order. You would have to go through and generate those plots yourself and then make an assessment of that plot to figure out what's really going on. And I think we had one lab where students would occasionally get negative orders. And that was always good to talk about because you can actually get negative orders. Not with the type of problems we work, but actually there are models that give negative orders that are what are considered inhibiting reactions. So what happens is that you add more and more reagent that slows down. And when physically this happens if you have a catalyst, because everything has to bind to the catalyst, but they don't necessarily stick equally. And so what will happen is that if you put too much of one compound in there, it will push off the other reagent so they can't react. And this is what's considered a self-extinguishing reaction. So you want to keep the concentrations low enough that they're both sticking to the catalyst and can react. But if you start throwing more and more in there, ultimately what will happen is that one will push the other reagent off the catalyst and they can't react anymore. And this gives rise to non-power law relationships. Generally what happens is that you have a complicated mechanism where you have things that are having to bind to each other, and that will give you like fractional orders or negative orders. All right, I give about 10 more minutes for the 11 o'clock crowd to show up. Second order kinetics, are you doing 1 over the y-intercept? Also make sure it's not one of those like weird problems where it's so dependent on the decimal points you use. So could you give me a specific homework set? We can work through it. Typically what I see for incorrect answers for the starting concentration for second order is just 1 over the y-intercept. Test 2 study packet. Bring it up. Time and rate, concentrations from time and rate loss, page 5. So we'll do the one at the bottom of the page, concentration of bromine, and I'll bring it up so people can see it. So the question is, what's the concentration of bromine if its consumption follows second order kinetics? With our starting concentration of bromine being 0.76 molar, and the rate constant K being 0.193, 1 over molarity times unit of time here is hours, and the time here that is elapsed is 7.3 hours. So in order to, I'm just going to bring up Excel just so I have the space to work in. For this, the kinetic model, 1 over A minus 1 over A naught equals KT. This is the more useful form of the second order. There is one I present that is kind of rearranged to give concentration versus time. I just don't find it horribly useful. If you've got to memorize one, memorize that one. But we've got, if we rearrange this, we get 1 over starting concentration equals KT plus 1 over the starting concentration. So the concentration is 1 over KT plus 1 over the starting concentration. So K in this case, 0.93. Time here, 7.3. And starting concentration is 0.76. So when I plug that into Excel, I get 1 divided by 0.93 times 7.6 plus 1 divided by 0.76. And concentration I end up with is 0.12 molar. This is at least conceptually makes sense. We expect the concentration to go down. Now let's see if I actually downloaded the answer packet. Let me download that from the course website really quick. Yeah, I get 0.12 in the key as well. So yeah, to figure out the concentration of bromine, you just need to rearrange the second order equation. So bring that over, and then just plug in your numbers and take 1 over that number. Hey, you're welcome. Again, there's another formula. I have it just for completeness. But it's just algebraically rearranging this. Actually, this comes from this, but rarely do we ever worry about this. This is used most commonly for the kinetic analysis, so you might as well just use this formula and just rearrange it for the times that you're happening to solve for concentration versus time. That page represents the practical end of it. The whole reason we're doing all this kinetic modeling is ultimately we'd like to be able to predict what a reaction is going to do. All right, other questions? Now I'm looking through the discussion boards, and just to make it clear, the discussion boards are more meant to hit on the harder topics. Do go through the study packets, do go through the homeworks. Those are going to give you a much better feel of what's going to be on the exam. The discussion boards are more to kind of make sure you're getting the bigger ticket items, but again, everything that you see in the packets, everything you see on the homeworks, those are all fair game on the exam next week. Now, there's no gotcha questions. Like, if you can do the packets and you can do the homeworks just fine, you're going to do just fine on the exam. It looks like your exam is next week, based on the discussion boards. And then next week, we're going to start getting into thermodynamics, and we're going to start getting into equilibrium. We give you about another 5-6 minutes, and if no one's got any more questions, we'll just sign off from there. Get your diagrams to reappear. So are there images not showing up in the discussion board? Best option for that is to open the discussion. So click on your. So when you get to the discussion board and you open it up in a new tab, and that should keep the old figure up there so you can still look at it when you're answering the question. I found particularly Blackboard's kind of buggy when it comes to some of my figures, or pretty much figures in general. So yeah, I've had it suddenly delete figures on me for no particular reason. It's like it can't find the file. So yeah, that would be my best advice, is that when you go to answer the discussion board, right click and open it up in a new tab or a new window. And this way you have the old figure there. Even if it does disappear, it's not going to disappear in the old browser window. Another option is that you should be able, if you hover your mouse over the right side of the figure, you should have the option to open the figure in a new window. This can be hit or miss, but generally it should open up the figures in a new window so you can actually see them large and in their own window. Oh, that for kinetic model. That kinetic model one's being really obnoxious. Hold on. fix it at this point. And I'm working with the group that's developing organic chemistry for online, and yeah, we're starting to see a lot of these issues because with organic, they're very figure heavy, and it gets really annoying when you spend a lot of time writing a discussion board and then you suddenly can't find the figure, or the figure is completely illegible in Blackboard. So it doesn't help you because I developed this course in the spring, and now that we've kind of formed a collaboration with Online Organic, we're starting to see all these little issues with Blackboard that we're solving, but we're getting better. We're learning little tricks like opening up a new windows, and we're learning new tricks about like, okay, keep discussion board open in one window and then answer it in another. Show how you do the graphs. Yeah, certainly. So let me switch it over to my desktop, and we'll go to dataset 4. So you're going to want to create your 3 columns. A few tricks in Excel. So the natural log function, you're going to hit the equal sign. The equal sign tells Excel that you want to call a formula. Natural log is just ln, and you click on the cell you're interested, close parentheses, and that'll give you the natural log. For 1 over, it's equals 1 divided by that concentration. Now, to fill the formula down, there's 2 ways to do this. The way I was traditionally taught is you highlight the cells and you hit Control D, and that fills down. Another option is that if you highlight these 2 cells, there's a little square here on the bottom right. If you click your left mouse button, hold down, and extend down, it will have the same effect, but what it's doing is that it's copying the formula down, but it's changing the reference. So in this cell, I said take the natural log of the cell beside it, and that's what it's doing for all of these. Now, the way to rapidly draw multiple graphs in Excel, draw your first one, so highlight the data. Excel is going to assume the first column is the X and the second column is the Y. So if you get them flipped, it's going to still treat them as X and Y. You want to go to Insert, and you want to go to the Scatter options. So on this version of Excel, Scatter is the bottom, but you definitely want to see the Scatter menu, and click on the first option. Change your chart title. And to add your trend line, you're going to right click on one of the data points. You're going to get an add trend line option. And in the menu that appears, you can click display equation on chart and display R squared. Now, here's how you rapidly draw them in Excel. If you want to plot other data tables, the natural log and whatever A, you can highlight. Or what you can do is click on your concentration versus time graph, hit Control C to copy, click outside the graph and hit Control V. And this is going to copy and paste the data. But if you click on the individual data point, so let's say we want to switch this to natural log of A versus time. If you click on the data points, you'll see it does a purple and a blue. You can actually grab the blue box and drag it over, and that will automatically update the data as well as the linear regression. And we can do it again for 1 over A versus time. We just paste the graph again. Do 1 over the concentration, just so we know which one we're working with. Click on the data, hover over the blue box until you get the 4-way arrow, and just drag it over to the 1 over A data, and that'll give you your 1 over A versus time plot. Now, if you're feeling particularly crafty with this, so this is data set 4, if you go to data set 3 and copy the numbers and paste them in, Excel is a live update program. So once you paste in new values, it updates. I'm pointing my finger at the screen like you can see that. It'll automatically update these formulas, which subsequently update these graphs. So that's another option, is that you can create one sheet that has all your graphs on it and just change the concentration versus time data. But yeah, once you've got the one Excel sheet set up, and this is the super powerful thing about Excel, it means a lot of super powerful things, you can just take the data, you can copy the sheet, just right click on it, say you want to copy it, create a new sheet, and just drop in data. And it's going to update the 1 over concentration data, it's going to update the natural log of concentration data, it's also going to update all the graphs. So you can just copy and paste the data and just start filling in the information that's being requested in the homework. The most valuable skill you can learn in this course is Excel. It is a skill that will carry on through all your other courses. And I've had several students tell it to me that, they like the stuff we learned, but really the most valuable skill they learned how to use is Excel. Yes, you're very welcome. All your homeworks were developed using Excel. So if you're curious about how these problems came about, Excel has a lot of features. Like I can make Excel do intermediate rounding. I can make it do a lot of things that kind of give me feels for how answers would diverge. All I have to do is put in parameters and it gives me new answers. It's super powerful. All right, any other questions? All right. If there's no more questions, we'll sign off for today. Another live stream tomorrow and Thursday. Again, feel free to email me any questions you have. Chat with me through Teams. And yeah, I'll see you all tomorrow. Thanks for showing up.